All right, class, welcome to section 6.2. We'll talk about exponential functions and their graphs. So this is a new kind of function that we hadn't discussed back in chapter 1. And as I mentioned in the last section, right, about inverse functions, we would talk about two very famous inverse functions of each other, the exponential and the logarithmic function. So here's the exponential function. Now, an exponential function is one where the variable is in the exponent. So this is what keeps changing. The base is fixed, but the exponent changes. So not to make the mistake to confuse an x squared with a 2 to the power of x. In the quadratic function that we were discussing back in chapter 3, what keeps changing is the base. So we keep taking numbers and squaring them every single time. Whatever it is that we're talking about, we're squaring that value. In other words, we multiply it to itself. In an exponential function, the base is fixed. What keeps changing is the exponent. Take 2, raise it to the power of 2. Take 2, raise it to the power of 3, -1, whatever it is. So the base is the same. The exponent's the one that keeps changing. So that's the difference. So in an exponential function, the exponent is what our variable is. Now, of course, you might be familiar with this name, or we've used it before. B is the base, and this is fixed. In other words, constant, it doesn't change, right? But the variable is the exponent. So we'll talk about domain and range in a minute. The kind of like I would call it the toolkit function, the easiest exponential function is 2 to the power of x. So let's see how we get the graph of it. Now, exponents can be anything they want to be. We could have positive exponents. We could have negative exponents. I have posted for you as a textbook 6.0 exponents. So if you need review with that, you are welcome to read through that section, that textbook section. You should know about exponents, but again, you can review through it if you're unfamiliar. Left it there. So let's see what happens if we ever have an exponent of 0. Hopefully you remember that anything raised to the power of 0 always equals to 1. And of course you have calculators to help you through this. So you can always verify all of these facts with your calculator. Put anything to the power of 0, well, aside from 0. 0 to the power of 0 is actually undefined. But there it is. 1, if x is 1, 2 to the power of 1 is 2. If x is 2, 2 squared is 4. If x is 3, 2 to the power of 3 is 8. Of course, you can put decimal numbers. I wouldn't know them off the top of my head. I would have to use my calculator. So that's why I just pick integers. Negative exponents. If you remember, a negative exponent really means a reciprocal. So what we do is anytime you have a negative exponent, you put that value in the bottom to make the exponent positive. Because again, you can't multiply 2 to itself -1 times. That makes no sense. But an exponent is, of course, a repeated multiplication. 2 to the power of 3 means 2 times 2 times 2. We know how to do that. But with negative exponents, we wouldn't. So we fix negative exponents, make them back positive, just by putting them in the denominator. So if you're not familiar with these two rules, well, here they are. -2 the same. 2 to the -2 is 1 over 2 to the power of 2, which is 1/4. So 2 to the -3 is 1/8, and so on and so on. So if I start plotting these points, 0, 1, 1, 2, 2, 4, 3, 8, -1, 1/2, -2, 1/4, -3, 1/8, what you see is happening is the more we move into the negative values, the closer and closer the graph gets to the x-axis. So 1/16, 1/32, and so on and so on. However, as you notice, and then as soon as we start moving into those positives, the graph explodes. So it's increasing faster and faster. So because every time we're moving to the right, the values are doubling up. So we went from 1, 2, 4, 8. The next one would be 16, way, way up here. Okay. Now, when we pick an exponential function, this is very important. The base must be a positive value. So we will never talk about exponential functions if the base is a negative value. 0 also. So we'll keep the base strictly positive. Okay. So again, 0 to a power of x, that's always 0 again, unless you're talking about 0. So we don't want that. Negative values, we don't want to have a base that's negative, again, telling you on the side. Because then, if you remember, a 1/2 exponent really means a square root. And then we couldn't have negative numbers inside the square root. You can have it to the power of 3, that's fine, but then you can't have it to the power of 4. So you have to start a bunch of it. You can put in your graphing calculators, by the way, or in Desmos. You would see the Desmos trying to start graphing f of x is negative 2 to the power of x, but then you'll see it will just soon collapse because it has some plot some values and then it's undefined, and then plot some, then it's undefined. So and can't deal with that. Also, if you have an exponential function that's 1 to the power of x, 1 to the power of x is always 1. 1 to the 0 is 1. 1 to the 1 is 1. 1 squared is 1. So 1 to the power of x is really the constant function 1. That's a constant function, not an exponential function. We talked about those back in chapter 1. Okay, so therefore, there's some restrictions on our base. Base must be always a positive number and not equal to 1, because again, a base of 1 would lead to a constant function. All right. Now, since our base is positive, even if we're plugging in negative exponents, as you saw, a positive number raised to a negative exponent is still a positive value. So as you actually see from your graph, the domain is all real numbers. In other words, the exponents can be positive, negative, decimals, whatever they want to be. However, the range is going to be values that are strictly positive. So as you see, the graph is all above the x-axis. There is no negative answers at all. There's also no 0 answers. So this graph is going to get closer and closer to the x-axis, but it won't touch it. So these values that we get for y are never going to be 0 or negative. As a matter of fact, we just talked about these in the previous chapters. The x-axis is a horizontal asymptote. So y equals to 0 is a horizontal asymptote. So that's what our graphs are going to have. And so they will all have a horizontal asymptote. We'll shift them left and right and up and down. So as we will go through these graphs, I'm going to ask you, give the equation of the horizontal asymptote, give the domain and the range of each of the functions. Okay, so these are important features of an exponential graph. Okay, so let's move on to the next exponential function, 1/2 to the power of x. So as you see, our base is definitely a number that is positive and not equal to 1. So let's see what kind of values do we get if we make our base be 1/2. Same thing. I'll go through just a few, pick some positives, some negatives. 1/2 to the power of 0, anything to the power of 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/2 times 1/2. And again, put in your calculators. That's going to get you 1/4. 1/2 to the -1. Again, a negative exponent just takes the reciprocal of the base. So that's 2 to the power of 1, which is 2. And 1/2 to the -2 is the reciprocal to the power of 2. So that's a 4. So that's what negative exponents do. They turn the base into a reciprocal. So here it is. Let's plot these points. So I have still 0, 1, 1 with 1/2, 2 with 1/4, 3, by the way, would be 1/8, -1, 2, -2, 4. By the way, -3 would be +8. So 1/2 to the -3 is 8. If you were to put here a 3, you'd get 1/8. Okay. And so on and so on. So as you see, of course, we still have a horizontal asymptote. That is the x-axis. So y equals to 0. The domain is still all real numbers, and the range is still 0 to infinity. So the two graphs are very similar, except for one is increasing and the other one is decreasing. So the first graph keeps going up, up, up. The second graph keeps going down, down, down. As a matter of fact, these two functions are symmetrical about the y-axis. They got flipped about the y-axis. And that's simply because, let me take this to the side and show you how one is really just the transformation of the other. If I take 2 and raise it to the negative x exponent, yes, then that's the same as 1/2 to a positive x. So a negative exponent just makes the reciprocal of the base. So basically, the 1/2 to the x is just 2 to a negative x. So what happens when in a function we change x's to negative x's? So all our positive x's are now negative x's and backwards. So that's just simply a reflection about the y-axis. So that's what we learned as one of our transformations, right? Make x to, or put a negative to the x. That makes the graph reflect about the y-axis. And that's exactly what happened here, right? With these two graphs. Okay. All right, so as we've seen with all the functions so far, well, there are only 2, there could be a coefficient, not these factors, yes, that's what I meant to say. There could be a coefficient in front of the function, which determines the orientation of the graph based on its sign. So what I mean by all the functions so far, the quadratic had an a in front, the polynomials had an a in front, the rationals, the radicals, right? So we always had this extra a value that we sometimes had to find using mostly the y-axis intercept, yes? So let's say, so what I mean by this is if we look at x to the 4th, we know the orientation of it is that of a quadratic function, yes? But if you have a -3x to the 4th, what does the negative do to it? It flips the graph around, yes? So that coefficient makes a huge difference. So here are our graphs based on these two values, a and b. So b for the base and a for its coefficient. So here it is. If, first of all, the base is a number more than 1, like the 2 to the x we discussed here. So if the base is a number more than 1, then your graph will be increasing. Now, it also depends on if a is a positive value or if a is a negative value. So if your exponential function, let's say, for example, you might have a 3 times 2 to the x. What kind of orientation does that have? Well, that simply means your graph is going to go up because the base is more than 1, and you multiplied it by a positive, so its orientation will stay the same. So in other words, the graph will maybe increase or get stretched vertically by a factor of 3, but it's still all positive, so it's going to stay above the x-axis. However, if you multiply your function by something that is less than 0. So for example, you might deal with a negative 3 times 2 to the x. So your graph here has to reflect about the x-axis. So then the graph will be down in the quadrants 3 and 4 because your graph from before was multiplied by a negative, so it flips down. So again, in both these cases, the domain is still all real numbers. The range has changed, though, from 0 to infinity to negative infinity up to 0, right? So everything is negative because you multiply all values by a negative. So that's kind of the graph you get. So now if you are having an exponential function with a base less than 1, again, if a is positive, so in other words, you have maybe a 3 times 1/2 to the x, so your function is decreasing and staying above the x-axis. So again, increasing, decreasing. 1 is what we would talk about exponential growth. Oops, that's what I meant to say. And so this one's exponential growth. And this one is what we would call an exponential decay. So the values, if the base is less than 1, the values keep going down. Now, of course, if you multiply by a negative, all those values that keep going down but are negative are just going to start increasing. So if a is less than 0, we flip this graph above the, below the, wrong way. We have to flip this graph about the x-axis, and then it's becoming increasing. Yes, this shape. So something like this. Okay. So here are the shapes of the graphs of exponential functions. Okay. All right, so let's use transformations. It's always best. You can make a table of values if you want. But it's best to use transformations because you want to keep in mind where the horizontal asymptote is going to go. This one's super easy. The first thing I'm going to graph is that basic 2 to the x exponential function. And I know that your points might still not be there yet, but again, think about 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. 2 to the negative 1 is 1/2. So here it is. My 2 to the x function I graphed for you on the previous pages. And then there's only one transformation in it. And the -1 simply makes the graph shift 1 unit to the right. Yes, as always. So I'm taking these bubbled in points that I've had and just shifting them to the right. So it's asking us to find the domain, which is always all real numbers. The range, as you see, it's still above the x-axis, so it's all positives. And of course, we still have our horizontal asymptote. That is the x-axis, so y equals to 0. Remember, horizontal lines always have equation y equals to some number. All right, here's one that has a couple transformations. So I'm going to first start with a 1/2 to the power of x. And again, 1/2 to the power of 0 is 1. 1/2 to the power of 1 is a half. 1/2 squared is a quarter. 1/2 to the negative 1 is 2. 1/2 to the negative 2 is 4. So just as I graphed this one on the previous pages for you, it's a decreasing exponential decay function. Let's see. I'm going to take the 1/2 and raise it to the x plus 1. So this is going to make the graph shift 1 unit left. So what I have right now, I'm going to take these points and moving them 1 unit left. Okay. And then finally, as we've been doing so many times, we are going to minus the 3. So as always, I like to start with the x transformations and then all the y transformations. So minus 3 makes all those points go 3 units down, right? Okay, so take these points, moving them 3 units down. Now keep in mind that as this graph moved 3 units down, it doesn't mean it's going to go now all of a sudden down to negative infinity. All these points had to go down 3 units, but your graph still has this horizontal line that it can pass. It's just that our horizontal asymptote that was y equals to 0 now moved down 3 units to y equals to negative 3. So this is our new horizontal asymptote, and that's why it's important to graph these functions using transformation so you don't just all of a sudden start crossing over your horizontal asymptote. You still have to keep the graph above or below a certain line. And that's important. So here it is. The domain is all real numbers. The range, as you see, is above this line, so from your horizontal asymptote up to infinity. And of course, your horizontal asymptote is the one that stops the graph at negative 3. Okay, so the range has lots to do with that horizontal asymptote because it's from that line all above or from that line all below if we happen to flip the graph. Okay, so let's try this a couple more times. This time, as you see, again, a couple transformations. I'm multiplying by negatives. So let's see what all of this does. Also, look at this. I am starting not with the 2 to the x, but with another basic function, 3 to the power of x. So how does the graph change if we change that base to, instead of 2, a 3, a 4? Well, let's see. Let's start with some of these points. Well, 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the negative 1 is 1/3, and so on. So the shape is the same as that of 2 to the x, except for a higher base makes the graph go up faster. So we say, same as with x squared versus x to the 4th versus x to the 6th, that the higher the exponent, the closer the graph gets to the axes, right? So it gets narrower and narrower. And the same thing happens here if we increase the base. Okay, so in other words, 4 to the x would come in even narrower. Oops. So the shape is the same as long as the base is something more than 1. Yes. As long as the base is something more than 1, we do have the same shape. All right, let's see. What is the next transformation? There's two y transformations here. Number one, that we multiply these y values by a -3. Okay. Okay. And then add 1 to it. So remember, when it comes to y transformations, you have to follow the order of operation. So in other words, multiplication first and then additions or subtraction. So for this, we just basically multiply any y coordinate by -3. So 1 goes to -3. 3 is going to go down to -9, somewhere way down here. 1/3 is going to go to -1. 1/9 is going to go to -1/3, and so on. So what did this do to the graph? It stretched it vertically by a factor of 3, so it's way more stretchier, right, vertically, but it also flipped it about the x-axis. So all your positive y's are now negative y's. And finally, +1 simply means lift this whole graph 1 unit up. So shift all these points 1 unit up. Now be very careful. As you lift all these points, there's still a barrier. As again, our horizontal asymptote that before was the x-axis, now the horizontal asymptote moved up simply 1 unit at y equals to 1. So the domain is all real numbers. The horizontal asymptote is y equals to 1. So again, the point shifted up, and so did this horizontal asymptote. There's still a barrier. You can't move past 1. Therefore, the range, as you see, is -infinity up to 1. We always start lowest possible value to highest possible value. So it's never backwards. So it's not 1 down to -infinity. Anytime we write an interval, it has to be lowest value, comma, highest value. So we go left to right or down to up. Okay, this one's going to be tricky because that -3x exponent. So here it is. I'm first starting with y equals to 2 to the x, right? So our base is 2. This is our basic function, 2 to the x. Okay, well, we'd graph that a few times. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the third is 8. 2 to the -1 is a half. 2 to the -2 is a quarter, and so on we go. Okay. All right, now there's an x transformation here. So let me do this one in blue. What do I do with the -3 multiplied to the x values? So remember, anytime we're dealing with an x transformation, we have to do the exact opposite. So instead of multiplying all the x coordinates by -3, we will divide all x coordinates by -3. Okay, there's a radical function that we did with this as well. So here's my x coordinate of 0. 0 divided by -3 is still a 0. Here's my x coordinate of 1. 1 divided by -3 is -1/3. Here's an x coordinate of 2. 2 divided by -3 is -2/3. Here's an x-coordinate of 3. 3 divided by -3 is -1. So what's happening is, of course, this graph is going to get flipped. -1 divided by -3 is positive 1/3, by the way. So what happens to the graph is, you see, first of all, it got flipped about the y-axis because all your positive y's are now x's are now negative x's. So we flip the graph about the x-axis, okay? But we also compress the graph horizontally by a factor of 3. So the graph got squished in towards the y-axis 3 times over, right? So the graph got compressed, so squished into the y-axis by a factor of 3. Okay, it's always best just to think of, yes, multiply the y-coordinates by -3. Just take those y or x coordinates, depends who is changing, and do that operation to it. And finally, here's our last one. Take the graph from before, the 2 to the -3x, and subtract 2 from it. So the -2 simply is going to take all these points and moving them 2 units down. Now what also is going to move 2 units down is the horizontal asymptote. So we, same as we couldn't pass below 0, we now cannot pass below -2. So our horizontal asymptote also moved down 2 units, or barrier. So when I write domain, again, that's easy, all real numbers. Range, as you see, this graph, the red graph, is all above -2, not touching -2. So therefore, we put a parentheses and not a bracket at -2. And our horizontal asymptote is y equals to -2. Okay, so hopefully these graphs, again, over and over again, we're using our transformations we learned in chapter 1. They came in so handy in all the other types of graphs and functions that we've been talking about. So, again, by now, they should be coming super easy to you. Okay. So, let's, aside from graphs, kind of like go backwards, right? Here's the function, graph it, find points, do things. Now let's go backwards, as we've done with every single one of our equations: linear, quadratic, polynomial, rational, even, we didn't do that to the radicals, but yes, pretty much every function that we've been, absolute values, we've done the same thing. So here's the equation. It might have a number at the front. Remember the a value that we've had in front of all our functions. So find the equation of an exponential function. This is the form of an exponential function, reminding you of, so kind of like find me the equation of a line. Here's the form of a line. Find me the equation of a quadratic function. What did we call those things? H. Here's the equation of a quadratic function, right? So we know the form that we had to write the equation in. Okay. Now, the form that we're going to write an exponential function in is right here. So we know it passes through the point of coordinates 0, 6. So that simply means that if I have an x of 0, the y comes up to be 6. So let's plug that in right away. Y equals to b to the power of 0, and y is 6. So remember, f of x always stands for y. So I'm going to plug in a 6 for that y and a 0 for the x. Now that's very nice, because anything raised to the power of 0 equals to 1. And there you go. I already found my a. Great. Now I'm going to use the second point to find the b. I already know that a is equal to 6, so I'm going to use that. So in place of y, I put 750. In place of a, I put 6. I already found a. There's no reason to hide it again. B is still the one that I have to find, and x is 3. Great. So to get to that b value, I'm first going to divide by 6. And that should be 125 or something, but I'll check. So 750 divided by 6, yeah, 125. B to the power of 3. Well, we've done that. How do I get rid of a power of 3? Well, its inverse operation is the cube root. So the cube root of 125, by the way, is 5. So b is 5. So here is my function. F of x is 6 times 5 to the power of x. Now, it is very nice when one of our values, one of our points that we're given is the y-axis intercept, such as that 0, 6 right there. If we know the y-axis intercept, it makes it so much easier because we get to plug in 0 for x. None of these are the y-axis intercept. And see how nicely out of that immediately I found a, right? So this didn't happen here. So it's going to be a little bit more algebra that we're going to use. So here it is. 3 over 2 for y is equal to a times b to the negative 1. And at the same time, 24 is equal to a times b to the power of 3. Okay, so what we have here is pretty much something that we call a system. I have an a and a b, and I don't know how to solve it. So we haven't really solved systems prior to this, but basically what we want to do is somehow combine them and solve for a and b. So one way to easily solve these equations is something called substitution. So you can solve for a in one of these variables and then replace it there. Another way, again, maybe not, don't see these, but you actually could divide both these equations on both sides, and that's going to cancel out your a's because, well, it's a common factor. But let's just say you can pick whichever one of these equations you want. And solve for a. So I'm just going to pick the bottom one. That seems like a more easy looking equation because, well, we don't have fractions in it and we don't have negative exponents. So to solve for a, I just simply divide both sides by b to the third. And I'm going to take this a and replace it in here. So in other words, 3 over 2 is equal to a, which is 24 over b to the third, times b to the negative 1. Now we just simply have to remember how we deal with exponents. How do we get to put these b's together? And by the way, what does a b to the negative 1 mean? You can also subtract exponents if you have this is one of the rules of exponents. If you divide numbers with the same base, you subtract the exponents. So here you have it, right? You can think of it as, wait a minute, I thought negative exponents simply means that I have to put that b in the denominator with a positive 1 exponent, and now you can see how you get a 24 over b to the power of 4, because again, multiplying numbers with the same base, you get to add up their exponents, so you get to see how both those b's are in the denominator. And still, I need to solve for b from here. I know I picked a trickier one. You can cross multiply. Now this is a much better looking equation, or you can do what we've learned in the last chapter. You can multiply both sides by the least common denominator, right? So that will put the 2 over to this side, multiply to 24 is 48. Then we'll cross out the 2's and we'll put the b over to the side, multiply to the 3. And from here, it looks way more normal. We'll divide both sides by 3. And then I'm going to take the 4th root out of it. And then the 4th root of 16, if you put this in your calculator, number that multiplies to itself 4 times to give you 16 is 2. Okay. So I still need to find a. And a was 24 divided by b to the 3rd. This time we found b first. And 24 divided by 8 is 3. Okay, so here's our function. A is 3 and b is 2. So maybe you wouldn't have thought of it with those funny answers, but you can test it, right? 3 times 2 to the 3rd, that gives you 24. 3 times 2 to the negative 1, that gives you 3/2. So, all right, we will look at many more applications of exponential functions, but I wanted to talk about the first one right here, which is money growth or decay. So money, populations, bacteria, that's a population, bacteria, they grow exponentially, usually. So let me introduce to you some of the money grow or decay formulas. Okay, we talk about interest, we talk about principal, and yes, interest rates and time. So the simple interest formula simply says if, let's say you invest an amount of money which we call a principal, and that's P, at an annual interest rate R. So R is the interest rate that the banks are offering you if you invest that amount of money for a time T, which definitely has to be in years to match the annual interest rate. Then the amount of money that you will earn which we call an interest, is I. And I filled up all that space and should have definitely left myself more room. So let's say for this problem here, you might invest $1,000. Maybe you have $1,000 laying around. And the bank offers you a 5% annual interest rate. So in other words, every year your money grows by 5% of what you have. And you leave the money in there for 3 years. Then how much interest will you have earned at the end of the 3 years? That's simple. Calculation, all you do is multiply the 1,000. Now, you don't multiply by 5. It doesn't get 5 times as large. 5% means $5 per $100. So $5 per $100 simply means a 0.05. So if you learned to change percent numbers into decimals, 5 per 100 is 0.05, and then times 3. So 1,000 times 0.05 times 3 is $150. So at the end of 3 years, you will add on $150 to the $1,000 you already had. Okay. Now that's the boring, simple way. Usually things get a bit more complicated. We definitely, as consumers, let's say we invest some money with a bank or wherever you might put money in, mutual funds, things like that. You might say, hey, you've been using my money throughout this 3 years, right? So banks lend money out, right, to businesses, other people. And they earn a lot more than the 5% they might offer you. And then you say, well, you've been earning money on my money throughout this time, so I want to start earning interest sooner, not just the end of my 3 years. So what happens is we can say we would like to start earning interest earlier, and then basically earning interest on the amount of interest we've earned. So that's what the compound interest formula does. So again, P is going to stand in for that principal amount of money that you are investing. R is the interest rate. So yes, it is kind of funny that they start calling now R with a lowercase, where in the simple interest formula we use an uppercase, but that's just really how it is. It's still the same interest rate. T is still the time, same story. And by interest rate, we mean annual interest rate. And by time, we mean the time in years. Okay. And then N is the number of compounds per year. And I'll explain what this means in a minute. Now, A is the amount of money at the end. And by this, I mean A is going to equal to the principal amount of money that you invested plus the amount of interest that you have earned. So here for this story here, A would be the $1,000 you invested plus the $150 that you earned. So in the end, you will have $1,150 in your account, right? So you're not losing your 1,000. A is what you have at the end, principal plus amount of interest earned on your principal. So let's see what that N really means. Let's say $3,000 is invested at an interest rate of 5% for 5 years. And again, this 3,000 is your principal. Find the amount in the account if interest is compounded annually. So compounded annually means how many compounds per year? Once a year. So even if you left the money in there for 5 years, that still means that we didn't wait for the interest to be given to us at the end of the 5 years, but rather at the end of each one of these 5 years. So here it is, the amount of money you'll have at the end is going to be, according to this formula, we can put all that in our calculator, is 3,000. 1 plus R is 0.05 divided by N, which is 1, to the power of 1 times 5. Okay. You can change this a bit if you want to help yourself. Put things in your calculator. 0.05 divided by 1 is 0.05. Plus 1 is 1.05. So point is, that's what we're going to put in our calculator. So 3,000 3,000 times, and I'm going to put in a parentheses, 1.05, close the parentheses, to the power of, so you use that little hat, 5. Okay. So at the end, we will have $3,828.84. So anytime we write dollar amounts, they always should be to 2 decimal places for your cents. Okay. So in other words, basically you've earned another $828 at the end of this whole thing. Now, what if interest is compounded quarterly? Let's just solve this problem with a simple interest. What would we have earned in interest if we let the bank just give us the interest at the end of the 5 years? So we're starting with 3,000. The interest rate is 0.05, yes, and then we leave the money in there for 5 years. How much interest would we gain? So 3,000 times 0.05 and times 5, that's 750. So if we let the bank just give us the interest at the end of the 5 years, we would have only earned $750 on our $3,000, yes. This way, at the end of the year, we figure out interest, add it to the principal, and reinvest the full amount. Same thing. So basically, you start earning interest on the amount of interest you've earned each year. So as you see, the difference is much higher. Now, what if we say the interest is compounded quarterly? That means how many times a year? Well, there's 4 quarters in a year. So same thing, put all of this in your calculator. But this time, it's because the interest rate is your annual interest rate. After 3 months, right, that's a quarter, you're not going to earn your full 5%. You're only going to earn a quarter of that 5%. So after 3 months, you are only given 1.25% in interest. However, the amount of compounds, the amount of times we keep figuring out the interest and adding it to your principal is 4 times as much. So I'm going to leave this and put it in the calculator as it is. I want 3,000 in a parentheses, 1 plus 0.05 divided by 4, just like that, to the power of 4 times 5. Of course, we all know 4 times 5 is 20, but even if you didn't know, you can just put all of this nicely. And so here is your answer. So as you see, there's a little bit more than what we got before, not that much. So from $28 to $46, well, it's something. Not that much more, but definitely more. Okay, and here is one more, compounded daily. Fine, daily means N is 365 times a year because there's 365 days in a year. So we'll put the same thing in our calculators, but this time in the N is 365. So let's see how much more money we would get. So 3,000 times 1 plus 0.05 divided by 365, just like that, to the power of 365 times 5. Okay. Well, about $6 more, almost. Not that much more, and there's a lot more compounding in this period of time, and yet that just pushed only $6 more. But it's more. So what if we want an infinite amount of compounds per year? So we're like, fine, I don't care if I don't earn that much more. I want the most of my money. So I want the bank to compound my money, my interest, not every day, not even every hour, every second, every split of a second, constantly. We call that continuously. So let's change the formula for a bit, and we'll call by m the n over r from before, or the r over n. That's what it was in there. We'll call the n over r by m, so therefore r over n is 1 over m. It's the reciprocal. So I'm replacing that in. N, if m is equal to n divided by r, if you cross multiply, the n from before is m times r. Okay, so again, don't worry about, I'm just trying to show you where the formula comes from. I could just give you the formula and you don't have to worry. Again, none of these formulas have to be memorized. I just want to show you where it's coming from. So now if you look at this expression only, 1 plus 1 over m to the power of m, and you start putting in values for m into this expression. Obviously, we want more and more compounds. So the more and more we put in for m, and you can put this in your calculator, as you see, the answers you get are not getting to be too large. They start sticking to the same type of value. So you see the 2 repeating, 2.7, 2.71, 2.718, 2.7812. So these values get more and more towards one number. That's 2.7. Yeah, it's a value between 2.7 and 2.8. This value has a special name, and its special name is E. So E is this 2.71828, by the way, blah, 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 blah. So more and more as we let m get closer and closer to infinity, so infinitely large, these values here get closer and closer to the number E. And we call that number the Euler number for the guy who discovered it, which is Leonhard Euler, a Swiss mathematician. Okay, so let me show you our calculator. Do you see somewhere here an E value? Yes, it's a little bit hidden. It's right here with the ln, which is another button that we're going to talk about in the next section. So here it is. I'm going to use second E. So e to the power of 1, which of course would mean E, is this 2.718281828. It's a irrational number. It has infinitely many non-repeating decimals. It might seem as if it's that 281828, but it's not. You can put in your computers and get a lot more decimals for it. Again, our calculators only give us so much every time. So see how these values all stop in the same place, whatever many digits, it's 10 digits every time. It won't give you more than that. So that's E, okay? Now, the way we change our formula is that as n gets infinitely large, that whole highlighted in yellow piece I have right here for you turns into an E, right? This whole thing turns into just the number E to the power of RT and the P at the front and the A. So I'm replacing the whole 1 plus 1 over m to the power of m with E. Okay, and here's our formula. So let's take this amount of $3,000 invested at 5% for 5 years and see what's the most we can get if we ask the bank to compound the money continuously, not once a year, not once a quarter, every 3 months basically, not every day, but all the time, every split of a second. So how do we put this in our calculator? So here it is, 3,000 times, 3,000 times, and see the E button, so you go to second e to the x, and so immediately puts an exponent, as this E value always shows up with exponential expressions mostly, so that's why they didn't just put E, but put an e to the x for our convenience. And I have a 0.05 multiplied to 5. And so, yes, if you compare it to the last value we got on daily, it's very similar. So we actually made 7 more cents as we round up. So in other words, that's the most we could get. 3562, I believe, right? 3862. 3852. 0.076, so 0.08. 3852. Yes. All right, here it is. That's the most we can make. Now, exponential functions with base e are going to appear the most in higher mathematics. So an exponential function with base e is a number just like pi. It's a famous number. That's why it has its own button on your calculator. But nevertheless, even though we use a letter to label it, pi is maybe a little more familiar because at least it's not a letter and you don't think it's just going to be a variable, right? But e is just an irrational number, just like pi. It has infinitely many non-repeating decimals. I know about this many for it. Pi, I only know the first two. But really, they are both irrational numbers, infinitely many non-repeating decimals, and they're both so famous and so widely used in mathematics that they have their own button on a calculator. Okay, so it's called the natural exponential function. Its graph, remember, e is 2.7, so it's really going to be e to the 0 is definitely a 1. E to the 1 is about 2.7. So somewhere here, e squared, 2.7 squared, whatever it will give us. So the point is e to the x is really just an exponential function that's increasing. It's somewhere between a 2 to the x and a 3 to the x exponential function. That's its graph. So here, last thing for today, I'll just show you. Ooh, I didn't want to, here. I don't want to delete all of these. So I'm going to clear this one. And I'm just going to put e to the power of x for you to graph. And there it is. Again, e to the 0, see how it crosses a 1, right? E to the 1 is about 2.7 something, right? Well, wasn't quite a 1 yet, but yes. And so on and so on. So here it is. That's exponential functions for you. Keep getting closer and closer, but it's not going to pass the x-axis. It looks as if it's on the x-axis, but it's staying above. All the y's are positive. No matter how far back you go, all the y's are going to always be positive. And then, yeah, and then crosses at 1. And then it keeps going. So that's it.